So we have so far looked at the spinodal curve. So we looked at basically the double well potential, right? This double well potential. So at lower temperatures we got double well potential, but at higher temperatures we basically got something like this, right? A homogeneous solution, right? We got a homogeneous solution, and we also basically found a common tangent. So in the case the common tangent here, because it's a single curve, we found that if I just do del gm del x equal to 0 and find the solution numerically, then I'll basically get these points at different temperatures, right? This is drawn at a particular temperature, and so as you go to lower and lower temperatures, the curve will be more spread out, and finally what we'll see is a phase diagram where you will basically have and this is something, the phase diagram that I have drawn already, right? So basically if I look at the curve, and then we looked at another free energy curve, and there I had some problem, right? Some issues came in drawing a tangent line, so I have corrected this and I'll demonstrate that. So before that I'll just recollect that we have done. If you look at the other one, we have already looked at this phase separation, and right, this one we have already done, and we had these different free energies, right? And at lower temperatures we had this double well type of curve, and which has positive free energies, and you had this minima, and then we solved all of these points, right? We solved all by looking at the first derivative. We solved all these points by looking at how these curves at different temperatures cross the x-axis, right? Because wherever it intersects the x-axis, and that is the solution, right? That is the solution. Fx equal to 0 is the solution, right? These points are the solution. So you can see at high temperatures you have only one intersection, while at low temperatures you have one intersection here, one is here, and another is here, right? So you have like corresponding to the maximum, corresponding to the minimum, right? So if you now collect all of this information and then you plot them, what you basically get is this. So if I just quickly go through this, so I have this curve, then I had this guy, and then I plotted the locus, and plotted this one. This one, and after this I came and plotted this one, and if I plotted this one, what I got is a miscibility gap, if you can see. So around 962 or so there is this critical temperature, right? Around 962 you can basically do omega by 2r, you can apply omega by 2r, and you will get the critical temperature at which. So here inside you have two phase coexistence, like this is your temperature in Kelvin, and this is your composition from 0 to 1, and you can, as you can see, you have got what is called a miscibility gap, right? This you have got what is called a miscibility gap. This is the phase diagram. So this phase diagram, how do we obtain? By basically calculating these points, right? Basically calculating these points, or basically what I have done here, because it's a single free energy curve, so mu a alpha equals to mu a beta, or mu b alpha equals to mu b beta, in this case basically translates to finding the minima and the maxima of these curves, basically del gm del x equal to 0 for different gms at different temperatures, right? So this is gm at 400 and this is gm at 1300. So what is the thing? At 1300 you have only one minimum, right? It's a homogeneous solution, while at 400 you have basically two minima and one maximum, and these two minima correspond to the phase separated mixture of two phases, right? It's a phase separated mixture of two phases. So basically one is a A rich phase and one is a B rich phase, and this, as you can see here, this is showing up here also, where I am doing the del gm del x equal to 0. So it gives you two solutions, right? These two solutions and this one. So basically I collect all of the solutions and I plot them. So basically at 400, as you can see, you have these two points. Again at 500 you have slightly reduced the points. 600, again the gap has slightly reduced, right? The compositions, the coexistence compositions are slightly nearer. Again, as you go to higher and higher temperatures, the coexistence compositions come slightly nearer, closer and closer, right? This coexistence composition. So this one and this one, say for example. Now here at TC, basically, you do not have above TC, you do not have any coexistence. Now you have a single phase, like above 960. If you are at 1000 degrees, say for example, there is a single phase with a composition of 0.56, right? With us given compositions, right? This is what I've done, and you can smoothen it further. You can smoothen it further using spline, and that's what I've done. And you can smoothen it further. The curve, this blue curve basically gives the smoothened phase diagram. So smoothened one and the red one with the data, they are not much different. And as you can see here, you have a TC here, right, around 960, and above 960, it is a single phase, it is a single homogeneous single phase solution. Now, we had this problem, having done that, we then presented another problem. So, I'll just go to the problem. The problem was this. So, we have been given this data, where TMA is the melting point of pure A, TMB is the melting point of pure B, G0MA is the free energy of pure A, and 0MB is the free energy of pure B, and then omega L, that is of liquid, is negative, but it is a regular solution because you have a negative regular solution parameter. Negative regular solution parameter basically indicates that you will have more AB type of interactions will be more favorable than AA and BB type of interactions. On the other hand, when omega is equal to 0, that is for the solid is basically approximated as an ideal solution. And we have also given the model for the solid and the liquid. So for solid, it is minus XHGMA 0 plus, so this is basically for the pure, this is basically for the standard state. So if I look at that, this is for the standard state, you multiply with XA. So basically this is basically the pure phase, right? So this is for the pure A or the standard A, right? That's why there is a XHGMA 0 minus XHGMA 0, and then this is basically minus T delta S mix, and this is basically delta mix, right? Delta HM mix. Here also you have a delta HM mix, but that is equal to 0, right? Delta HM mix equal to 0. Now, there are open source softwares, for example, PyCalFat, which looks at these different models, and basically looking at the models, it solves for this mu A alpha, say mu A liquid equals to mu A solid, and mu B liquid equal to mu B solid. So PyCalFat does that, and basically at different temperatures it does that at different temperatures, and basically gives you the phase diagram. Similarly, it's called calculation of phase diagrams of CalFat, right? In CalFat, you use more sophisticated models than the regular solution models. You use something like compound energy formalism and stuff. So if you want to look at compound energy formalism, you can look at books on CalFat method, right? So books on CalFat method by Agren and by Bo Sundman and all. So you can look at different books, and you can go to different papers on this CalFat method, and there is this PyCalFat calculation of phase diagrams. Again, you have very sophisticated free energy models, and if you have free energy models for different phases, then the phase coexistence is dictated by this chemical equilibrium, that chemical equilibrium condition. So basically for all components you solve them. There is also another commercial software called Thermocalc, and there are several other commercial software like MTData or Pandat. And for academic use, for example, Thermocalc gives you an academic free edition. So the academic, so it's a free academic version. So basically you can download the free academic version and you can use it, and you can see that, you will see basically at the back end you have all these different models for the solids and the liquids, for the ordered solids, or even I have discussed, right, for ordered solids, how to basically take into account the site fraction. So all of these are there. You have more sophisticated model with this based on compound energy formalism, and basically it is given by a special polynomial called Ridley-Kirchner polynomial. So basically they are using such, right? Here we are using regular solution model, but the idea is same. The idea is simple. So once you have all this data, right, all this data, the pure data, the pure elements data, the component data, and you have all the interaction data, everything. So basically what you do is you draw this free energy composition curves and find the common tangents, because these are the common tangent equations. So this is what I want to tell you, that these are the common tangent equations. So if I now, without much ado, we'll go to the, because in the previous lecture when we tried to demonstrate, there was some problem, there was some issue with one command, and I have fixed it, and I just want to quickly demonstrate, okay, how you basically go ahead with this numerical model. So I'll go to this G versus X curve. So I can can again show you. So basically if I yeah, so I have cleared everything, but what you have to understand is I have carefully coded this. So I have carefully taken a composition range between point 10 to the power minus 8 and 0.99999, like up to so basically this is 10 to the power minus 8, and this is like zero point 0.9 up to 8 decimal points. However, I haven't taken 1 and 0. This is because you have the delta S mix. In delta S mix, you have this log terms, right? And if log 0 is undefined. So I have taken as small a value, as close a value to 0, as close a value to 1 as possible, and I am plotting this. And I have all this data. Omega S is 0, that means the solid phase is an ideal solution. Omega L is minus 20,000, it's a regular solution with AB bonds more favorable. And then you have GMS 0, that is the pure A, and GMB 0, that is for the pure B. You have the free energies, and you have the melting point of A, melting point of B, and you have the models, right? You have the regular solution models for the liquid phase and the solid phase. So I am basically doing that. So if I plot that at a particular temperature, say 1000, I basically see, and the blue curve, so I am using the blue curve for the solid and the red curve for the liquid, and if you can see, there is a common tangent highly likely here, right? If you solve the chemical equilibrium conditions here, so basically you will get at 1000 Kelvin, there is on this side, on the B rich side, you have a coexistence. However, on the A rich side, you basically have the liquid phase as the low energy phase, right? And the A rich side, right, on this side, you have the liquid phase, which is the red free energy, is the low energy phase, right? But on the B rich side, you have a coexistence, right? Now, if you go further, so if you go further down, say for example, I go to something like 800 Kelvin. I now see a very similar coexistence, although in this case now I start seeing, say for example, here the solid and liquid at this composition has become nearly the same. So this is basically the melting point of pure A, right? This is basically at, this is at 800 Kelvin, right? This is basically 800 Kelvin. So I have taken the temperature to be 800 Kelvin. So basically at 800 Kelvin, obviously the solid and liquid, right, at pure AN, the solid and the liquid will have the same free energy, right? Because 800 Kelvin is the melting point of pure A, right? But if you see here, you have again a coexistence. However, the coexistence curve is such that you are now slightly less B rich, right? That the coexistence is slightly less B rich. But I will draw the common tangent here. I will not solve the chemical equilibrium conditions numerically, but I will draw common tangents here for these different temperatures. Again, I can use some temperature like 600. Now you can see that there is coexistence on both sides, right? On the A-rich end, you have this common tangent possible, and there is another common tangent possible, right? So basically, I want to plot these tangents and I want to see. So basically for that, I require these functions. So I am going to draw a tangent to the liquid, and I will try to make it a common tangent to the solid to find this coexistence, right? This common tangents will basically give me these 2 points, and these 2 points will indicate the equilibrium compositions of coexistence, right, at different temperatures, right? And you can basically take all of these and then plot them, and you will get the phase diagram, temperature composition phase diagram. So I have my derivative. So I want to write the equation for the tangent. Once I have written the equation for the tangent, Now at 1000 Kelvin I am looking at the tangent, right? I am drawing the tangent to the common tangent, the coexistence. So as you can see here, the common tangent is drawn around 0.82 here, and this is likely something like very close to 0.94 or 96 in the solid case, right? So this is one coexistence that I got, right? And this is at temperature 1000. Now I go to temperature 600. Say for example, I go to temperature 600, where you saw two-phase coexistence on either side, right? On the A-rich side as well as on the B-rich side, and I plot them together. And I get this, right? I get this. So if you look at that, see, hopefully the recording is going on. Yeah. So as you can see here, you have at 600 Kelvin, you have a two-phase coexistence here, which is between say liquid composition of 0.23 and the solid composition of around say 0.1 or so. And then on this other side, you have another solid liquid coexistence, which is for the liquid composition of 0.54. So somewhere here, 0.54 is somewhere here, and this is at some solid composition of 0.8, right? So now you are going to a temperature like 480. So I have already studied this, and if you look at 480, you will see a very interesting point here. You see in the middle there is a solid liquid coexistence at a single composition, like near 0.4. Not in the middle, not middle is like 0.5. So here it is like close to 0.4, basically 0.41 or so. You start seeing at 480 that the solid and the liquid have the same energy. So basically this is a solid liquid coexistence at a given composition, right? The solid and liquid do not have two different compositions but the same composition, right? So if it is so, now if with all this information, if I want to draw the phase diagram, so if you look at the phase diagram, I have schematically shown it. So if I have schematically shown it, and if you look at that, yeah, so this is your likely phase diagram for that particular model. So you have this phase diagram. This is your temperature axis, this is your temperature axis, and this is your composition axis, and composition goes from 0 to 1, and this is the pure A, where this is xb, basically this is xb, and this is pure B. So on the right hand side you have pure B, and on the left hand side you have pure A, right? And this is the most likely. So as at 1000, as you can see, there is a single coexistence. So this is the liquid phase, and this is the solid phase, and this is liquid plus solid, and again you have a liquid plus solid. Now as you can see at 480, this is a special point where basically you have this special point where liquid and solid of same composition coexist, right? So you have a liquid solid same composition coexist, right? This is something, this type of phase diagram you will see is only possible when you have this liquid and solid caving into a single point. This is possible. It can be also happening on the upward side, right? This is possible only when one of the solutions, one of the phases like liquid or solid, has to be taken as a regular solution. If both are ideal solutions, you basically get a Lenz type diagram, like type 2 type of phase diagram, right? Type 2 phase diagram. Now, having said all of these, you know how to basically calculate mu A and mu B, and you can basically, if you know how to calculate mu A and mu B, say for example, this is the mu A formula, this is mu B formula, and then basically you have done this, right, from the tangent intercept method, and even without tangent intercept method, you can analytically derive these equations, and now you can basically, for each phase, you can you know mu A and mu B, and then you can equate mu A alpha equals to mu A beta and mu B alpha equals to mu B beta. That is the conditions of chemical equilibrium to actually numerically solve them and at different temperatures, and you can basically calculate the phase diagram, right? That's what Pike, Alfred and others do, right? So that is one thing. And second thing that I want to tell you is basically, again, basically if it's a non-ideal solution, you have a regular solution, for example, you can also calculate the activity by equating it, right? This activity you can equate, because mu A equals to mu A 0 plus RTL and AA, mu B equals to mu B 0 plus RTL and AB, and remember, only thing, you can do it for the solution also, because say for example mu A minus mu A 0, is basically mu A in the solution, mu A0 in the pure state is delta Ga bar, right? Delta Ga bar is the partial molar free energy of mixing for component A. This is delta Gb bar is partial molar free energy of mixing for component P, and that is nothing but RTLN AA for delta Ga bar. For delta Gb bar, it will be RTLN A, right? And you can plot all of these, right? You can basically find all of these, and you can equate them, and you can get basically, say for example, RTLN AA. I am getting it. This is the expression omega xp square plus RTLN XA. Now RTLN AA, basically again I can write it as RTLN gamma XA, which is omega xp square plus RTLN XA, and this is RTLN gamma A plus RTLN XA equals to this. So basically I get the activity coefficient gamma A. So what is the equation? This is the equation. Now you will see, you can basically explore when you have this regular solution free energy with the positive heat of mixing. You can basically see that there is a critical temperature Tc equals to omega by 2R. This is something we have shown, and this is something we have shown by equating the second derivative of the free energy to 0, right? So basically we got this Tc value. Now you can also find out gamma A at this critical temperature or gamma B at this temperature. That means you can also find out the activity coefficient at the critical temperature. Now I'll go to, so far we have been looking at non-reacting multi-phase, multi-component systems. Now non-reacting systems, you have the Gibbs phase rule. If you include the pressure also, say you are including gas phase, then you basically, your degrees of freedom is C. C is the number of components minus number of phases plus 2, right? However, when you have a reacting system, you have to look at the species, because you have reactants and products. So for example, you have this type of reaction, A plus B gives you C plus D, right? This is an example. So this is, or more generally it is like AA plus BB produces, and you have this. So both are possible, right? Reactants to products or products to reactants, right? So it goes to C moles. So this is like the stoichiometric coefficients. C moles of C. So A moles of A react with B moles of B, produce C moles of C or C molecules of C and B molecules of B. So this is one reaction. This is one example reaction. In such reacting system, the Gibbs phase rule, that is degrees of freedom, is written in a slightly different way, where we do take into account also the number of constraints, which is basically the number of independent relations or reactions, number of independent relations or reactions among intensive variables other than thermal, mechanical and chemical equilibrium. So these independent relations are nothing but the number of independent, we can call it number of independent reactions. And S, instead of C I am using S. S is the number of different species or constituents. So for example, so species is an entity that is distinguishable from other species by its chemical formula. The species can be charged or uncharged. For example, H2 and OH minus, right, the hydroxyl ion are different species. Carbon dioxide and CO3 2 minus, right, this CO3 2 minus, this is a charged ion, right, a charged negative anion, right, so negative ion. So these are different species, okay. However, H2O gas and H2O liquid, H2O, the formula is the same, so they are same species but different phases, right. H2O gas and H2O liquid are basically water vapor and water, liquid water, and they are basically the same species because their formula does not change, but they are different phases, right, liquid and solid. So for example, if you think of this decomposition of calcium carbonate, it produces calcium oxide solid and carbon dioxide is gas, and you have basically three species, right? CaCO3, CaO and CO2, because they have different formula. And you also have three phases, two solids and one gas. And if you see, there is one reaction, right? There is one reaction. So if you look at the degrees of freedom, it is 3. S is 3, right? In this case, S is 3, and then you have minus P minus R plus 2, right? So instead of C, you are using, so this is a species-based Gibbs phase rule is what you generally use, right, in a reacting system. Now, in a reacting system, you have to understand there is this delta G reaction that is basically given by, so this is basically nu I are the coefficients like small a, small b, small c, small d are the stoichiometric coefficients, right, for the reaction. So delta G reaction is related to summation of mu I, right? Mu I. And basically, if mu I is greater than 0, that is for products. So the convention is for the product side, you will use, say, if you have again this reaction, AA plus BB goes to the product CC plus DD, then basically here the stoichiometric coefficients are like plus C and plus D, and here they are reacting, so this is minus B and minus C. So if you look at that, so you have minus, so nu I equal to 0 for inert specimen which does not basically react, right? Which does not, for all inert species nu I, you take the nu I value to be 0. Now once you have this delta G reaction, you can also find out, so you have this delta G reaction, and you can basically find out that something called equilibrium constant, or this is basically called a law of mass action, okay, where A is the activity of species and K is basically an equilibrium constant. Now if you see, if I have these reactions, for example, A plus B, that is one molecule of A reacts with one molecule of B, the gas phase to produce two molecules of C in the gas phase, right? The total energy is basically given by mu A plus mu B minus 2 mu C. Now at equilibrium, this has to be equal to 0, right? That means mu A plus mu B minus 2 mu C has to be equal to 0. Or we can write this mu A as mu A 0 plus RT ln PA, because it's gas phase, so partial pressure of A, mu B 0 plus RT ln PB, and this 2 mu B C 0 plus 2 RT ln PC. Now if you look at that, the delta G0 is basically 2 mu C 0 minus mu A 0, right? So product minus reactant 2 mu C 0 minus mu A 0 minus mu B 0 basically is going to be my delta Z0, which is basically given by, if I take this, do this little rearrangement, so it's given by RT ln PC square. See, this is on the product side, product is on the numerator, and this is PA and P. So basically delta Z0 comes out to be this, and this is basically called RT ln Kp. Kp is the equilibrium constant. So ln Kp is minus delta G0 by RT, and Kp is nothing but Pc square by Pa Pb, or we can write it as, if my total pressure is capital P, then I can write Xc square P square by Xap Xbp, so I get X square by Xxb. Again, this is not general, this is for a special case, okay, but we can basically write a generalized equation like that, right? Now think of this, when you do equilibrium, what you do, you extremize entropy, right? You maximize entropy, and you use something called, if you use an isolated system and you give something called isolation constants. So these are called isolation constants. Like total energy cannot change, total volume remains fixed. So these are called isolation constants. Now once you have these isolation constants, only thing, for non-reacting system you can also tell the number of moles, the total number of moles does not change, right? That's for a non-reacting system. That means dnk equal to 0, right? For a non-reacting system you can add this additional, we can have this additional constant. However, for a reacting system you cannot do that, you cannot use dnk, so there is a possibility that dnk is not equal to 0, right, for a reacting system. So basically, although the total number of atoms of I of each element in the system will remain conserved, total number of atoms of I, right, of the species, say for example, I have total number of starting atoms of carbon is say 100, then it will remain 100 even after reacting. Although the number of atoms for each element in the system will remain constant, but dnk is not going to be 0, right? Because moles of, say, in this reaction, for example, you have A plus B going to 2C, or A plus B going to C, for example. So you have 1 mole of A and you have 1 mole of A, and it went to 0 moles of C. So basically, if I think of this, so this is my initial, and then later, say for example, 1 minus, say for example, if there is an extent, so defined by say some parameter eta. So if I say that, so basically A reduces by 1 minus eta, okay, and eta is basically the number of molecules, right? If you have, or a fraction, eta is something called a fraction or degree or extent of the reaction. So if you have that, so if at equilibrium you have like 1 minus eta and 1 minus eta, and here you have eta. So basically now here you had starting, you had 2 moles of A and B. Now you have 2 minus 2 eta plus eta. So basically 2 minus 2 eta plus eta is your number of moles, right? So basically it is basically has become 2 minus eta, right? Now 2 minus eta and 2 are not same, right? So D and K is not equal to 0. However, the total number of atoms of the species I, right? This is for each species I. For each species I, the total number of atoms of each element. So I is basically, so each element in the system, right? Total number of atoms of each element. So basically, if I say, instead of call it element, say for example, and total atoms of each element E in the system, total number is conserved. Total number of atoms is conserved, but the total number of moles is not, right? The initial number of moles and the final number of moles will be different, right? They cannot be the same when you have a reacting system, right? So as you can see, another thing, when you are doing this, you are going from I, that is my initial state, to the final state, right? So basically you have the final state which has, say for example, some extensive parameter. This extensive parameter is a function of Tf, T final, P final, N1, N2, and this is basically Z, which is T initial, P initial, N1, N2. Now if you see, in case of non-reacting system, N1 and N2 I and N1 and N2 F are same, right? This basically means 1 and 2 are non-reacting or inert species. Now if I look at this dissociation reaction, say I2 goes to 2I, you have I2 which is constituent 1 or species 1, and I is constituent 2. So initial state you have Ti, Pi and N1 0 and N2 0, and in the final state you have Tf, Pf and N1 and N2. Now if you see N1, which is N1F, is not equal to N10. N2, which is N2F, is not equal to N2. So as a result, D and K equal to 0. That isolation constant, right, the differential of the total mole, the mole number of each species has to be equal to 0. That isolation constant is only valid for non-reacting systems, not for reacting systems, right? That is one of the very important thing. And another thing, when we look at chemical reactions, we stoichiometrically balance them, right? So for example, this equation, you have one CH4, one molecule of CH4 at reacting with one molecule of water will give you one molecule of carbon monoxide and 3 molecules of hydrogen, right? Now if you look at the stoichiometric coefficients, you have, this is reactant, so new CH4 will be minus 1, new H2 will be minus 1, new CO will be 1, and new H2 will be 3. Now if 1 mole of CH4 disappears, right, this is a reactant, right, this disappears, that means 1 mole of water must disappear, right? If this has to disappear, then this has to react with water, so 1 mole of water also must disappear, and 1 mole of CO must form, and 3 moles of hydrogen must appear, right? 1 mole of CO must appear or must form, and 3 moles of hydrogen must appear or must form, right? This is what we are looking at. So basically, if you look at the stoichiometric coefficients of methane, of water, these are minus 1, for carbon monoxide is 1, and for hydrogen is 3. Now as you can see here, so if I look at the change in mole number of CH4, if I look at the change in mole number of CH4 divided by the new CH4, and change in mole number of water divided by new water, delta NCO divided by new CO, and delta NH2 divided by new NH2, then these are all going to be equal, right? So basically what we are telling, you have this reaction, new 1A1 plus new 2A2 plus dot, and you have new 3A3 and new 4A4. So basically what we are telling is dN1 by new 1 because dn2 by equal to dn2 by nu 2 equal to dn3 by nu 3, right? Change in mole number by the stoichiometric coefficient, the corresponding stoichiometric coefficient is equal to the change in mole number of species 1 normalized by the stoichiometric coefficient for species 1 is equal to the change in mole number of species 2 normalized by the stoichiometric coefficient of that species, right? And then we can basically define d zeta as the extent of reaction. You can call it zeta. I think this is zeta, this is not psi. So, or this is psi. So, define the psi as an extent of reaction. So, it does not matter, right? This symbol basically might be psi or zeta, whichever it is, you can check. So, then dni is nu I d zeta, right? Or d psi, right? Nu I d psi is basically equal to dni, right? Where I goes from 1 to n. These are all species that are constituents. Now, if you have multiple reactions, say for example, then you have say m reactions, then you can write dnir, where r is the reaction, the number of reactions. R denotes the index for the reactions. I denotes the index for the species. I is the index for species. R is the index for reactions. So you have dnir equals to nu ir d psi r. So this psi r is the extent. It is the basically the extent of the reaction, right, or the degree of the reaction R, right? This is for the reaction R. Now, so then the total dni will be basically summed over all the reactions dnir, which is basically summed over all the reactions. dnir is nothing but nu ir, right? Nu ir is the stoichiometric coefficients for a reaction R times d psi r, and d psi r basically gives you the progress or the extent of the reaction. Right now, if you integrate this equation, basically from psi r equal to 0, ni equals to ni 0 is the initial state, right? Initial mole number to psi r equal to some psi r and ni equals to ni. Then basically what you get is ni equals to ni 0. So see, ni is not equal to ni 0, but some extra term, and that extra term has the extent of reaction. Right, this term comes in. So ni is not equal to ni 0 because there is a reaction, and in that reaction, all the species are not really. So these are not inert species, right? Ni, these are not inert species. If they are inert species, then this term does not come, right? So since they are reacting species, then ni, that is the final mole number for each species I, is going to be this plus this. Now, if you sum over all species, you will get the total mole number n, which is sum over all species, which is going to be again the sum of this entire expression. Now, if I do this entire expression sum, this is I equal to 1 to n ni 0, and this is sum equal I equal to 1 to n for nu ir, psi r, you have double summation, right? You have sum over the species, you have sum of the reactions, right? And as you can see, I equal to 1 to n nu ir is nothing but mu 1, right? So then basically ni 0 sum is basically, if I do, then basically this is total n, and this is going to be total n 0 plus r equal to 1 to m nu r psi r, right? So basically n is this, right? And n0 is summation of I equal to 1 to m, that is over all species at the initial state, and summation over all components or all species nu ir basically gives you nu r, and nu r is the stoichiometry coefficient for RF reaction, right? So another thing, as I told you, the individual atoms of each element, if you look at that has to be constant throughout the reaction, right? So basically NaI, so this is for I is the element, right? I is the element. So if I is the element, right? So instead of I, that's why I will call it E. That's better. So basically this is for individual atom of each element. So, and this becomes basically Xe, and this becomes Ne by n, okay, which is basically going to be this Ni0. So if you look at that, so for each element, individual atom of each element, that has to be conserved. So basically, if that is so, you can look at, so you call it I or E, does not matter. So right, this is for I. If I do it for I, the atoms of species I have to be, for each element have to be constant, right? So if I call it NaI, So have a look at this. If I call it I or E, does not really matter. What you get it, Xi equals to Ni by N, right? And Ni is nothing but NiO plus nu IR. It's IR, and you have N0, right? The total N is N0 plus nu R, right? So this is going to be your mole fraction for I, right? So for each I. So just have a look at this reaction. There are two reactions. Say you have two reactions here. So just as an example, you have CH4 plus water giving you carbon monoxide, one molecule of carbon monoxide and 3 molecules of hydrogen. This is reaction 1, and your CH4 plus 2H2O, 2 water, 2 molecules of water react with 1 molecule of methane to give 1 molecule of carbon dioxide and 4 molecules of hydrogen. This is reaction 2. Now if you see, the N0CH4 was basically 2 moles, right? You have 1 mole here, you have 1 mole here. So you have 1 plus 1, this is 2 moles. And for water it was 3 moles, but for CO it was 0, right? CO2 it was 0, CO it was 0, and hydrogen also it was 0, right? So basically if you look at that initially, if you tabulate all of these, so basically you have IR, and you are looking at the I is basically for the species and R is for the reaction. So nu 1 1, say for example CH4 equal to 1, right? CH4 I am basically calling it as species 1. So this is species 1, H2 I am calling it as species 2 or reactant 2, and then 3, 4 and 5 are the product, right? So if I now look at R equal to 1 and I look at nu I1, that is for each reaction. That this is for the reaction number 1, this is for the reaction number 1. So for CH4 or species 1, your coefficient is -1. For H2O or species 2, your coefficient is -1, right? For this is for reaction 1. So you have -1 here and -1, right? And for reaction 1, if you look at carbon monoxide, that is the species 3, nu 31 is +1. But nu 41, which is basically carbon dioxide, you see in the first reaction there is no carbon dioxide, so nu 41 is going to be 0. Nu 51 is again +3, right? 3 hydrogen. Now if you look at reaction 2, you go very similarly. Only thing is nu 2 is -1, nu 2 basically 2 is the species, right? Nu 2 there is a second reaction. So right, this is the second reaction. So nu T2 equals -2, nu 3 that is there is no carbon monoxide, so it goes to 0. Nu 4 is +1 and nu 5 is +4. Now if you look at that, you have therefore nu 1 is basically, you are doing it for nu 1 is basically that's the stoichiometry coefficient for reaction 1. So it is I equal to 1 to 5 nu I1, which the resulting stoichiometry coefficient is basically +2. Why? -1 plus -1 is -2, -2 plus 1 is -1, -1 plus 3 is +2, right? So it becomes +2. So nu 2 also, if you look at that, -1, -2, -3 and +5 is +2, right? So nu 2 also is +2. So for R2 also it is +2, for R1 also it is +2. So you have N0CH4 which is 2, which is N01, and N0H2 which is 3, which is N02, and then N0CO which is equal to N0CO2 equal to N0H2 equals to 0. So N0CO is basically N03, this is N04, and this is N05, right? Now if I have this, now if you put this formula, you can write NCH4 which is N1, right? N1 is nothing but Ni0 which is 2 minus, right, because nu IR is IR, and nu IR is basically -1, and here also, so for R equal to 1 also it is -1, for R equal to 2 also it is -1. So psi 1 is the extent of reaction 1 and this is extent of reactions 2. So basically you get NCH4 in terms of the extent of reactions as well as starting number of moles. Similarly for water it is 3 minus psi 1 minus 2 psi 2, right? You can see there is 2 water. So basically -2 psi 2. You can look at the chart. For NCO it is psi 1, right? Because you had 0. You started with 0 and you had psi 1 plus 0 psi 2. So it's equal psi 1. For NCO2 it is 0 plus 0 psi 1, right? See, so there is no CO2. See, in this case CO, for the reaction 1 there is 1 mole. But for CO2, For reaction 1 there is nothing, but for reaction 2 there is 1 mole, so you have side. For NH2 you have N5 which is 0, right? It started with 0, but you had 3 in the reaction 1 and 4 in reaction 2, right? You have 4. If you look at that, 4 in reaction 2, and these are all positive coefficients, plus. So total N is 5. So you are writing the total N, right? In 5 plus 2 psi 1 plus 2 psi 2. So this is at equilibrium, right? So now if that is so, now you can find out the mole fraction. So mole fraction X of species 1, species 2 and so on. So for species 1 it will be 2 minus psi 1 minus psi 2 by 5 plus 2 psi 1 plus 2 psi 2. Again 3 minus psi 1 minus psi 2 by 5 plus 2 psi 1 plus 2 psi 2, right? This is the total N. Now if I have that, if you add them up, you will see that these are indeed mole fractions because the sum of them goes to 1, right? So now if you look at the change in free energy, if you change, the only thing that you have is this isolation constant is no longer valid, but you have now this relation, right, where you have the extent of reaction here. So basically this becomes dg equals to vdp minus sdt plus this entire stuff, because nu, so you have d xi r and you have nu jr and you have this mu j dnj, and basically if you have mu j dnj and then dnj can be substituted as this one. So this is exactly what I've done. So dnj, so mu j remains, right, mu j remains as, so and this becomes mu jr. So you have mu jr d epsilon r, so d epsilon r is taken, and here what I have done is mu jr mu j. So you are basically looking at the change in chemical potential. If I look at that, if I do, so basically now what I am doing here, mu jr mu j d psi r. So basically I am writing G has now changed from P, T and N. It has now become P, T and psi 1, psi 2, psi n, right? If you have M reactions. Now if you do del G del psi equal to 0 for keeping T, P and other reactions, right? Other reactions other than the ith reaction constant. So only taking account just the ith reaction, the extent of reaction variable, right? This is called an extent of reaction variable or an internal variable. So with respect to this internal variable psi, for the reaction I am keeping T, P and all other reactions constant, right? I do not want other reactions to proceed, and this is has to be equal to 0 at equilibrium, and that basically gives me temperature and pressure are fixed. So that basically gives me a very interesting formula, and that is this, right? Mu j I mu j, and the summation mu a j r mu j, basically j equal to 1 to n, again j is basically the species, right? J equal to 1 to n mu j r for each reaction has to be equal to 0, right, at equilibrium. Now how to determine R? If a system contains E elements, and you have S constituents or species, then the number of independent conservation relations or reactions, right, number of independent reactions that can be written for the system are R equals to S minus E, right? If you know the S, that is the number of species, you know the number of elements that are existing, then you can basically find R. So if, for example, if you have 2CO plus O2 equals 2CO2, you have two elements, right, Cu and O, right? So you have two elements and you have species are 3, right? This one is on, this one is on, this one is 1. So basically R, that is the number of independent reactions, is going to be 1, right? And F also we know is going to be 1, right? So that's the idea. Now if you look at these three reactions, like C plus O2 equals CO2, 2C plus O2 equals to CO, C plus CO2 equals to CO. Now if you look at R equal to S minus E, so S is number of species are basically carbon, oxygen, carbon monoxide, carbon dioxide. However, if you look at the elements, you have only carbon and oxygen. So basically R, that is the number of independent reactions, is going to be 2. Similarly, if I look at Gibbs free energy, so the degrees of freedom based on Gibbs phase rule. So I am looking at Gibbs phase rule here. If I look at Gibbs phase rule, again in terms of species, you have 4 species, 2 reactions, right? 2 reactions, 4 phases, right? You have 4 phases, 4 phases, 4 species, 2 reactions, and you have plus 2, right? You have, because gas, right? You have to use plus 2. So basically it becomes 4 minus 4 minus 2 plus 2, which is equal to 0. So degrees of freedom becomes 0 when you take exactly the independent reactions, right? So this is something that you can see Because if you see, if you look at CO2 equals 3 plus O2, then basically 3 can be written in terms of 2 minus 1, right? Or 3 can be written in terms of 1.1, right? This reaction 1.1. So basically I have just reversed it, and to draw this first reaction I have reversed to write this 1.1. So 1.1 plus 2 will give you 3, or 2 minus 1 will give you 3, right? The reaction. So basically, if you see, so if you have reactions like multiple reactions, then R equal to, but you have only one unique reaction, or means only one independent reaction, then it becomes univariant, right? These are called univariant systems. If you have R greater than 1, that is the number of reactions are more, the independent reactions are more, then that is called a multivariant system. Right? And now you look at something called a chemical affinity. Affinity is basically a linear combination of chemical potentials, right? Affinity is nothing but a linear combination of chemical potentials. A is mu Jr mu J, okay, which is basically in this reaction it will be mu CO2 minus mu CO minus half mu O2, right? Mu CO2 minus half mu O2 minus mu CO, right? Now if you have A and you have now DNI, which is basically mu Jr, and this is the extent of reaction R, right? Extent of reaction R. Here R is only 1. So DnCO is basically nothing but minus nu, right? Minus nu. And DnO2 is minus half Xy1, right? This is DnCO is minus Xy1, this is minus half Xy1, and DnCO2 is Xy. So basically, but you can see here that DnCO is this, DnCO is this, DnO2 is also, DnCO2 is also this. So these and these are equal. So if you see, DnCO is minus DnCO2, right? Because DnCO is minus Xy1, DnCO2 is plus Xy1. So basically DnCO is nothing but minus DnCO2, or DnCO2 is minus DnCO. Again, DnO2 can be written as also minus half. You can see minus half zeta 1. Zeta 1 is basically, so basically you can write minus half DnCO plus 2 DnCO2, right? So we can do that, right? So minus half zeta 1, so is basically going to give me minus half common DnCO plus 2 DnCO2, right? How did this come? This comes because you have minus half Xy1, right? Minus half Xy1 is basically 2 DnCO2 minus DnCO into half, right? 2 DnCO2 minus DnCO, right? Because DnCO is going to be minus Xy1. So this is minus Xy, this is plus 2 Xy, and this is minus half. So you basically get minus half Dn. So DnO2 is minus half DnCO2. DnCO is minus DnCO. So basically, although there are 3 components of 3 constituents, only one can be used independently, right? If I use NCO2 independently, I can express NCO in terms of NCO2, I can express DnO2 in terms of NCO. So, and the condition of equilibrium is that chemical affinity goes to 0, right? Mu CO2 minus mu CO plus half mu O2, right? These are the reactants, right? And therefore, I have this minus, the stoichiometric coefficients are negative, right? So, I have taken the negative common, so this becomes minus mu CO minus half mu O2, and this is plus mu CO2, and this affinity at equilibrium has to be 0, right? And at equilibrium also, the chemical potential of products has to be equal to the chemical potential of reactants. Now, if I look at the law of mass, so I'll now define what is called the law of mass action. I'm going pretty fast here because I want to basically tell you that the idea is very simple. So you have this reaction LL plus MM equals to RI plus SS. So these are your products and these are your reactants. So A is mu products minus mu reactants. So basically R mu R plus S mu S minus L mu M mu M. And then basically again you do the same thing. So you have now GK0, that is a pure flow, and you have this RTL. Okay. So basically you can write this as A equals to RTLN AK, AR to the power R, S to the power S, L to the power L, M to the power M, right? Basically, if you use this translation, right? This is the translation, right? And if you have that, you have A equal to, so you have all these terms, right? GR0, GS0, GL0, GM0. So this basically, the difference basically gives me delta G0. And this is RTLN, and this is AR to the power R, right? Because you see, this is RTLN AK, and mu k is RTLN AK. So basically, if you look at GR0, you are writing as GR0, and you have this term, right? You have this plus term. So you have mu k. So basically, mu r. So r times mu r is there, right? So r times mu r is there. So r times gk is 0, right? R times gk is 0, and you have, right, r times gr 0, s times g is 0, and so on, right? So basically, when you have small r here and you have capital R here, r ln ar is nothing but ln ar to the power. So you have this activity coefficient, which is basically A. So you have this affinity, right? This is the affinity, which is delta Z0, right? Delta Z0 plus RT ln AR to the power R, AS to the power S, this is L to the power L, and M to the power M. And you can define this term, this one, as Q. Now, what you have is A equal to delta 0, 0 plus RT ln Q. But K is Q equilibrium, which is QE, which is AR to the power R, AS to the power S by. So this is the activity of products, right, with the power as the stoichiometric coefficients, and basically this is at equilibrium. So basically what I am telling, at equilibrium equal to 0, that means delta G0 plus RT ln K, right? So delta G0 is minus RT ln K. So basically A is nothing but delta G0 plus RT ln Q, and delta G0 is minus RT ln K. So basically A, or the affinity of the reaction, right? This affinity is basically, again, this energy. Basically, affinity is nothing but energy, which is RT ln Q by K. Ln Q by K has no units, so this has a unit of joules per mole. So A has a unit of joules per mole, and this is called the Van 't Hoff isotope. Now, if you have, say for example, a gas mixture at 1 atmosphere pressure and 700 degrees Celsius, and you have this composition, say for example 0.01 is the composition of H2, starting composition, 0.01 is the mole fraction of O2, and you have H2O is 0.96. Okay, so this is basically the, so at 1 atmosphere pressure and 700 degrees Celsius has the following composition. So this composition can be the equilibrium composition. So you have 2H2 plus A2 is 2H2O, and delta G0 is also minus 440 kilojoules. Now you have K, which is minus exponential minus delta G0 by RT. Now if you see, delta G0 is this 440 kilojoules, so 440,000 by RT, R is this, and 973. So K is basically 4.2 into 10 to the power 23. Okay, so you check it. So it becomes 4.2 into 10 to the power 23. Now, if it is ideal solution, then Q is nothing but A square H2 by A square H2 into AO2 is nothing but A is equal to X, right? So A equal to X, Raoultian solution, A equal to X, right? Activity is equal to mole fraction. So it becomes A square H2 by A square H2 XO2, which is basically coming out to be 3.1 10 to the power 5. So basically Q by K is 3.1 10 to the power 5 by 4.2 10 to the power 23, which is 7.2 into 10 to the power minus 19. So Q by K is very, very smaller than 1. So there is a strong tendency for the products to form, because it is A equals to RT ln Q by K, right? So basically if it is RT ln Q by K and Q by K is very, very small, so basically, so as you can see here, RT ln Q by K is very, very small. So basically you will have a strong tendency for the products to form, right? So basically Q by K is greater than 1, then basically A greater than 0, that is products. So decomposition from products to reactants will happen, right? If Q by K is greater than 1, you have A greater than 0, then you will have a decomposition from products to reactants, right? If A is greater than 0, right? So, and if Q by K equal to 1, then you have A equal to 0. Now, if you have Q by K less than 1, then, so basically in this case, when Q by K is greater than 1, that means delta G is positive. So I go from reactants to products and I get A greater than 0. That means A greater than 0 means delta G is greater than 0, right? A is nothing but delta G, right? A is the affinity, it is defined as affinity, but it's nothing but the delta G, the free energy difference between the products and the reactants. So if you see if delta G is positive, then products to reactants decomposition is what is happening. So you basically see product has a higher energy than reactant. So to form products, you are basically increasing the energy of the system. As a result, instead of going from reactant to product, it will go from product to reactant. Right? It will basically go backward. Right? The reaction will proceed backward. If Q by K is greater than 1, if Q by K is greater than 1, or A greater than 0, that means delta G greater than 0, delta G product, but delta G is basically G products minus G reactants. Then if it is greater than 0, then it is likely that the products will decompose into reactants. On the other hand, when A equal to 0, then products and reactants are equally likely you have the equilibrium situation. Right? These are reversible reaction. A equal to 0 is reversible. Right? This is the reversible condition. The reaction becomes reversible. Right? We have discussed this earlier, but yeah. But if you see Q by K is less than 1, or here we had like Q by K is very, very small, right? Q by K is less than 1, whatever small it is, you will see. So basically, if it is less than, it is very less than 1, it is very, very small, then basically reactants will obviously proceed in the forward direction and reactants will react to form products. So this leads to formation. So reactants to products is called formation, products to reactants is called decomposition. Okay. So decomposition is likely when this is greater than 1, formation is likely, or products are likely when you have Q by K which is less than, or affinity is less than 0. Now if you look at extent of reaction, this is something that I want to tell again. You can calculate the extent of reaction in different ways. For example, you have this reaction A equals to BB plus CC, where C is the stoichiometric coefficient, B is the stoichiometric, and A. So if you look at the delta nu, that is a change in nu, basically this is, or basically you can directly call it nu. So some people call it nu, which is a sum. So basically it is B plus C minus A, right? Because B is positive, C is positive, and A is negative because it's reactant. So it is the reactant. So basically this is a dissociation reaction that is going on. So RTLN Kp is given by minus delta G0, and if A, B and C are gaseous, then you can directly use partial pressure. So it will be PB, partial pressure of B to the power B, partial pressure of C to the power C, partial pressure of A to the power A. Why? Because again this RTLN P comes in and you are doing like B RTLN PB is nothing but RTLN PB to the power B, right? You have PB to the power B, PC to the power C by PA to the power A, and basically if I have total pressure P, then I can write P to the power B x to the power B times P to the power C x to the power C by P to the power x to the power A. So basically we can write further, which is P to the power, so P is the total pressure to the power B plus C minus A, B plus C minus A is like P to the power delta nu, and then you have xb to the power B, xa to the power C by xa to the power A, where xa, xb, xc are the mole fractions. Now you can write this as P to the power delta nu, but xb is nothing but nb by total m, right? So nb by n to the power B, nb by n to the power C, n by n to the power A, and n is nothing but na plus nb plus nc. Now if you see n to the power 1 by n to the power B, 1 by n to the power C minus 1 by n to the power A. So again you can basically write this as P to the power delta nu, and you have 1 by n to the power delta nu. So basically you can group them together, you can have P by n to the power delta nu, and you have nb to the power P, nc to the power C, na to the power, where na, nb, and c are the mole numbers of A, B and C. Now if you look at Gibbs Helmholtz relation, del G by T del Tp is basically minus H by T square. So I am using it for delta Z0. So instead of G, I am using delta Z0. Then what I get is delta H0. So Arctic ln Kp is delta G0 minus delta Z0. So basically you get this very useful relation, which is called D ln Kp dt equals delta H0 by RT square. So basically now if I assume one special case where, say I am just taking an example of A equal to B equal to C equal to 1. So basically the reaction that I have is A decomposes to B and C. Now if I want to find the extent of decomposition or the extent of reaction, I will first look at the initial mole number, which is 1A and 0B, 0C. But now at equilibrium, say for example minus eta is the amount of moles or the fraction of moles that have been minus eta is the number of moles that have participated in the reaction at equilibrium. So you have 1 minus eta and you have eta moles of B and eta moles of C. So basically the total moles is 1 minus eta plus 2 eta, which is 1 plus eta. Now Kp is P, so basically P by 1 plus N to the power 1, right? 1 is delta nu. and you have eta times eta by 1 minus eta. So p eta square by 1 minus eta square is Kp. So p eta square by 1 minus eta square is Kp, where p is the total pressure, n eta is the extent of dissociation and does not depend on the total number of moles. Now if you see, eta square minus 1 minus eta by 1 minus eta square equal to Kp by p, right? So basically if I now take this guy here and take this guy here, so what I basically get, or I take this is fixed and just I take this guy here, then what I get is 1 plus Kp by p into eta square equals to Kp by p. Now what I get is eta square equals to Kp by p by 1 plus Kp by p, and you can do a little simplification which becomes equals to 1 plus 1 by 1 plus p by Kp, right? So this guy, basically this becomes this upon simplification. Now I know eta square as this, so eta, that is the extent of decomposition or extent of dissociation or extent of reaction, is nothing but 1 by 1 plus p by Kp. I am using eta here, I can also use xi. Okay, the meaning is the same, right? So I am basically looking at equilibrium, eta moles out of 1, eta mole fraction out of 1 has reacted. So basically I started with 1 or I started with n, it does not really matter, because the extent of reaction does not depend on the total mole number, right? So we can also look at gas mixture. However, when you do have multiple reactions, many a times when you look at, say for example, if you look at this assume ideal and you get the Kr1 and then you can get Kr2 and Kr3, and again you are looking at like Nt is NH2 plus NO2 plus NH2 plus NCO, NCO2 and CH4. Now one thing you have to understand, that number of atoms or elements are conserved, right? So basically Mj, so instead of Ni, right, where there was some confusion, I changed the notation to Mj. So Mj because K, so basically M is the gram atoms of element J, gram atoms of element J, and Bjk is the atoms of element J contained in the molecule of K, right? Bjk is contained in the molecule of K species, right, into Nk. Nk is the mole number. So Xj, which is the mole fraction of element J, is Mj by J equal to 1 to E, right? That is the number of elements Mj, right? Summation Mj. So you can basically do the same thing for Mc. For example, we will have 0 NH2, 0 NO2, 0 NH2O, but 1 NCO and 1 NCO2 and 1 NCH4. Similarly for O, if I look at the gram atoms of element of oxygen, right, gram atoms of oxygen, I have 0 NH2, 0, but I have 2 NO2, right, 2 gram atoms of oxygen. And then I have 1 gram atom of oxygen from carbon monoxide, 2 gram atoms of oxygen from carbon dioxide, right. These guys will remain fixed, right. MH again will have 2 NH2, right, because there are two atoms of hydrogen, and you have 2 atoms of hydrogen in H2O, and you have 4 atoms of hydrogen in CH4. So basically if Nt is 1 mole of gas, now Nt is 1 mole of gas, right? For Nt I have this formula. Where is that? Nt I have this formula. And I have also this number of gram atoms of carbon have to be conserved, number of gram atoms of oxygen have to be conserved, number of gram atoms of hydrogen have to be conserved. So this gives me 3 equations. And these 3 Kr1, Kr2, Kr3 basically gives me 3 equations. So you have 6 equations, you solve them numerically. So there are various software that are available, okay, with which you can basically solve this problem. So if you have multi-component gas mixture, reacting gas mixture, you will have multiple equations which you have to solve simultaneously, and in such case analytical solution may not be possible, and you have to numerically solve the equations to find the composition of the gas mixture at equilibrium, right? And when you want to do that, the additional equation comes from this, looking at the balancing the gram atom of carbon, that is totally there. So basically the gram atoms of elements. So what is not conserved is the isolation constant. As I told you, the total mole number does not remain constant, right? The total mole number can change. However, the number of, or the gram atoms, or the amount of atoms of each element that is there in the reaction, right? So what I am telling is M is nothing but the number of gram atoms of elements that are conserved. So if you have E elements, then you will have E conservation conditions, right? If you have E elements, you have E conservation conditions. So you have 3 elements here, C, O and H. So 3 conservation conditions that are always valid throughout the reaction. Whether you are at equilibrium, whether you are initially, it's always there. So basically the point is these three conservation of elements gives you three equations, the equilibrium constants give you three equations, and you have six unknowns. Say for example, you have like this one, so basically this one, this one, this one, this one, this one, this one. Right? So basically NH2 is unknown, or XH2 is unknown, XO2 is unknown, XH2O, XCO, XCO2 and XH4. So basically you can solve these six equations numerically to get these six conditions. Right? So and you can also have heterogeneous reactions where you can have like solids and gases together. So I will come to that in the next lecture, in the last lecture of week 2.